Hi friends, now in this session we'll talk about the reading number 1 regression analysis with the multiple variables, module number 3, model misspecification. In this module we have two discussions primarily. First is about the model misspecification, and then we have the second part of the module, which is the violation of the regression assumptions. So we will see what are these assumptions, what causes these assumptions, and so on. So here you can see like we are discussing this whole the part 1 and part 2 in the tabular format. Now, if you consider the curriculum, this module 3 is specified as a different chapter. Okay. This means if you get the case study, so all 4 questions should be based on these two concepts. And when you get tested on this type of area, the probability is or chances are you will be tested on the comparison between the say omitted variable versus the variables not transformed or scaling problem, and what are the effects of those issues. And that's why discussing it side by side gives you the more clarity comparison, and you will be able to remember it properly. Here memorizing what is the problem, what is the concept is most important. Okay, so you have to make sure you remember it. From the understanding perspective, this is easy to understand, not very difficult, but to solve or make sure you are able to solve question in the examination, you have to remember. Okay, there is no alternative for that. So let's start with the model misspecification. Model misspecification in simple terms is when you specify the model of the multiple variable regression, you have to think about the economic rationale. When you are deciding, okay, what will be the x1, what will be the x2, what will be the x3, there should be some rational or reasoning, economic reasoning behind it. If I had to give the say layman's example, model misspecification can be said as, like, say for example, we want to predict what is the height of the children in a particular area, and for that we are using the variable like the height of the tree. Okay, so imagine the 20 years back, that particular kid was born, and at the same time we planted tree near that area, and now the tree's height is grown in the last 20 years, and same happened with the kid also, right? Now here you are trying to establish the relationship of that tree and the kid. You will get the relationship, but there is no economic rationale for that. There is no logical rationale for that, because we are in the domain of finance and the economics. We look for the economic rationale. For example, if you want to understand the stock prices, then we should take the x variables, that is a independent variables like the EPS, maybe the volume of trading, and so on, and not just xyz random variable which is not related or which may not create the impact on the stock prices. Okay, so this is the reasoning behind the why the regression model should have the economic rationals. Okay, it should have the economic rationals, and if you specify model correctly, then the model is parsimonious. Parsimonious means this is the efficient and simple model. Efficient simply means you are able to get your job done with the less number of variables. That's the efficiency. See, you can get the job done with 100 variables, but if you can get the same job done in say 15 variables, then we will call this model as the 15 variable model as efficient. Maybe if you can do it with the 5 variables, then it is more efficient. So that's the efficiency and the simplicity of the model. The parsimonious model should perform well in sample and out of sample. That is, in sample as in the data you use to train that model, the in sample, and out of sample means the data which you want to forecast. Okay, so in sample and the outs of sample, I'm assuming from the like level 1 discussion you already understand the in sample and the out of sample, and this has to be done without violating regression assumptions, and this is the second part of the discussion. In the first part we will mainly focus on the misspecification of the model and not the assumption part. First misspecification is the omitted variable. You are omitting variable. You are not taking the variable in the regression model, which is important for that model, which is important to determine the dependent variable, and you are omitting that variable. For example, for the stock prices, you are outrightly ignoring the EPS. Okay, maybe you have some rationale behind it, but if you are doing this, then we have to see if that variable is an omitted variable or not, or you are compensating the EPS part with some other variable. Okay, so this is the thing here. then a variable is not transformed properly. This means the relationship between the dependent and the independent variable is non-linear, and you are inserting x1 as a linear variable. Okay, so you are not taking the log normal of that variable to make it the non-linear structure, and you are outrightly like just inserting that as a linear relationship. So that's the variable not transformed is the second problem. Scaling problem. Scaling is required to specify model properly, because if you consider the, let's say again, the stock price example, where the stock prices are the dependent variable, and for that you are using the independent variable, for which you take, say, one independent variable as the EPS, second independent variable as the dividend growth, and third variable as the trading volume. The trading volume can be in the lakhs or the millions. Okay, and on the other hand, EPS is in few dollars. Then if you consider the situation, okay, EPS in few dollars, then you have the really huge volume, and then you derive the coefficients and try to compare it, it will be difficult for you. So we will call this as, this is not the properly specified model, and there is a scaling problem. And we have to then see, like, if you don't scale model properly, whatever problems are there, okay, so which is again given here. Then incorrect data. So for example, you used, let's say, past 5 years data, out of which 2 years are relatable to next period. Okay, so this is the forecast period, and these 3 years are completely unrelated as in the economic condition for these 3 years was completely different, and for these 2 years economic relationship between the dependent and the independent variable was same as what you want to forecast, and you are taking 5 years, then you are using the incorrect data. You are taking the two economic regimes. This is known as a regime switching. So if you are taking the two economic different regimes, and some part of that regime or the major part of that regime is not relatable to this, that is the data on which you want to apply your regression model. Okay, so this is known as the incorrect data. So we have to see what is the meaning of the problem, what type of problem it creates. Again, as I said, like, you have to remember, mug up the concepts here. Even if you understand it, if you don't remember it on the exam day, it is going to create a problem for you. Okay, now first, the omitted variable bias, and very, very important, remember this, what is the omitted variable bias, because there is very fine difference between the omitted variable and the multicollinearity, which we will discuss later. Not including the x variable required as per the economic theory. Okay, simply you are not including here. One important note, for the sake of like shortening the text brevity, we will use independent variable as x and dependent variable as y variable. Okay, so we'll simply write x or y, and you have to always remember the x is for the independent variable and y is for the dependent variable. Not including x, that is the independent variable required as per the economic theory. We already discussed this, what is the concept here. And very important note, this omitted variable should be correlated. Remember this, it should be correlated with the independent variables to call this as omitted variable. If there is absolutely no correlation between the variable you have omitted and the other independent variables, we are talking about the independent here, not the dependent, okay, other independent variables, then by definition that variable is not the omitted variable. This is the primary condition for calling a variable as the omitted variable. Maybe there is a situation where there is no correlation between the variable which you have omitted uh, and the other independent variable. If that happens, as we discussed, no omitted variable, but there is also possibility like there is no correlation between the other independent variable and the variable you have included. Now here, instead of omitting, I'm saying included. The included variable may not have correlation, but omitted variable will be called as omitted only if there is a correlation between the other independent variables. Now remember, I am saying correlation, I am not saying strong correlation, I am not saying very strong or perfect correlation. We are saying simple correlation, the basic correlation. If it is strong correlation, then it creates a new problem, which is discussed in the multicollinearity part. Now to estimate, the example is very simple, to estimate the stock prices omitting the EPS. This is just an example. Again, there may be like models where the EPS is dropped. This is just for the explanation purpose. Okay. Now what happens if you omit the variable? Then there are effects on the coefficients, the B0, B1, B2. Okay. Effects on the coefficients. Coefficients are biased and the inconsistent. What is the meaning of biased and what is the meaning of inconsistent? You have to remember this. The bias simply means the expected value of these coefficients or the your independent variable after combining obviously with the your coefficient. In simple terms, the expected value of the estimate is not equal to the true value. Expected value of the estimate that is in the value you derived from the model. Estimate is not representative of true value. True value. Okay. Not representative of the true value or not equal to true value. It should not be like the exactly equal to, broadly speaking. Okay. This is known as the biased. If the coefficients are biased, then you won't be able to get the proper value, the true value, using these estimates. And what is the meaning of inconsistency? Inconsistency is the property which says, or the consistency is the property which says, as you increase the sample size, your model's accuracy, that the variable, independent variable's predictive power or the model's power, should increase. If the coefficients are inconsistent, it doesn't matter how big is the sample size, you won't be able to get the real picture out of that model. Okay. So this is the meaning of biased and the inconsistent. Biased is very different, inconsistent is very different. You have to remember what is the meaning of biased and what is the meaning of inconsistent. Then the effect on the hypothesis, it will also create the effect on the hypothesis, and the hypothesis is unreliable. You can't rely on the hypothesis. Whatever the null is rejected or failed to reject, you can't rely on it. Effects on the prediction. Prediction is also unreliable. Obviously, your coefficients are not reliable. How can the other part be reliable? Effects on the error term. The error terms will be correlated with the independent variable. The error terms in the model. This is your model. B0 plus B1 x1 plus B2 x2 plus error term. Okay. Now, this error term will be correlated to the independent variable, one or more independent variable. And this is again the assumptions violation. Okay. And here I'm assuming you already know the assumption because we are in the module 3. Assumptions are discussed in the module 1 and module 2, right? Now see here. Why this is happening? Let's say there was one variable which is this omitted variable. Okay. Omitted variable. Now, when you are not considering this variable in the equation, in the model, and this is correlated with these, so what will happen? The effect of this omitted variable will spill on these coefficients, that is a B1 and B2, and other effect will be on the error term. And because of these error terms and your B1, B2s, that is x1 and x2, will be correlated. Okay, that's the problem. And why this is happening? Remember, your model will try to extract, there is a relationship, right? So between the y and this whole model. Now, your model will always try to maximize or extract as much relationship as possible. Okay. If you're dropping variable like this, that relationship's impact will get captured by the other variables. And that's why this correlation we discussed, right? So there should be correlation between the two variables, that is the omitted variable and the other independent variables. So if there is a correlation, the effects will spill on the other independent and the error term, and that's how it becomes the connected or the correlated. Now, a simple remark, if the omitted variable is uncorrelated, the error term captures its impact. Okay. Now, if it is not correlated, then whole impact will be in the error term. Error term, always remember, what is this error term? Error term is the effect remaining model is unable to explain on y. Okay. So the effect which is not explained by this particular model on y, and this is captured in the error term. So if you are dropping the essential variable, which is the omitted variable in this case, this whole effect will get captured in the error term. And why is this happening? Because now this omitted variable is uncorrelated. There is no correlation at all with the x1 and x2. Okay. And if there is a correlation, then the effect will spill over on x1, x2 and error term. Error term will also capture some impact. Okay. So this is the point you have to remember. In this case, here B0 is biased, but B1 and B2 may be correct. Why B1 and B2 is correct or may be correct? Because remember, now we are assuming that the omitted variable is uncorrelated with the other terms, okay, other independent variables. And that's why there may not be any impact on the B1 and B2. Next is the variable not transformed. Now here, it is the transformation issue. You are using the linear relationship, whereas the actual relationship is the non-linear. Very simple. Okay. If you do this, then using the non-linear relation, if you do this, then again the same problem will be there: biased and inconsistent coefficients, unreliable hypothesis, unreliable prediction, and just one thing. Okay. So this particular part is not given in the curriculum. This is like the addition from my side. If you don't want to remember it, don't remember it. Okay, no problem. But just for the like additional knowledge purpose, you can think about it. And I summarized it. There are a lot of missing points in this summary. But anyway, because you don't have to bother about it, so no problem, right? Now see this. Unreliable, same like the and error term will be correlated with the independent variable, not very accurate. Okay, you can ignore this. Now, next is the scaling problem. So you're not scaling the variable properly. What happens if you do this? There is only one problem. The problem is with not scaling is that it results in the difficulties in interpreting the importance of the predictor. Once you get the B1, B2, your coefficients, and it is not scaled properly, one will look in the millions, another will look in the percentage. So how to compare this, right? So it is always better to scale the variables properly. The scaling part we will discuss properly in the machine learning and the big data topics. Here, just understand, don't look like, it doesn't look proper, okay? Like having one coefficient in the percentage and another in the millions. That's why the scaling is required. But remember, with scaling, all these things are unaffected. You are getting proper results, no problem with the results, okay? So your coefficients are good, that is unaffected. Hypothesis is good. Effect on the prediction is not there, and no effect on the prediction, no effect on the error term, because ultimately this is just a scaling issue. Then you are using the wrong or the incorrect data. You are using the wrong period, okay? And wrong period, simply as we discussed, you are using the different regimes for the forecast which are not related to the forecast, the required periods data. Okay, so in this particular case, again, you will have the biased and inconsistent coefficients, unreliable hypothesis, unreliable prediction. Okay, obviously the prediction will be affected, and again, not very accurate. Okay, so these you can ignore this, just ignore this. Okay, fine. So this is all about the misspecification. In this whole misspecification chart, most important part you have to remember is this. Okay, this whole table, then only this much and these 2 points. Okay, remember this much, you can ignore the rest. Now, next is the violation of the regression assumptions. First, if you don't recall the assumptions, please reread the assumptions, okay, and then watch this. Now, here we have 3 types of violations. First is the heteroskedasticity, then we have the serial autocorrelation, and then we have the multicollinearity. And you have to discuss these 3 assumptions in comparison, okay? Now, first is the heteroskedasticity. What is the meaning of heteroskedasticity? The variance of the residual is not constant across all the observations. If you see this on the graph, this is your x value and this is your residual value. Ideally, the situation should be, the plot should look like this, or maybe like this. Okay, so if this is the situation, this is known as the homoskedasticity. That is, you cannot predict the residuals value based on the x. Okay, fine. If it is heteroskedastic, very difficult word to pronounce, okay, then this will look like, so here we can clearly see the variance is increasing, variance in the residual is increasing as the value of x increases. Reverse is also possible. Reverse as in it may decrease like this. Okay, so here the variance is high, and as the value is increasing, variance is decline like this. Okay, in both the cases, we will call this as the heteroskedasticity. Now, here we have two types of heteroskedasticity, and let's see like which violation is which assumption is violated by the heteroskedasticity. We will call this as H, like again to shorten the discussion, the write up. Now, assumption violated is the variance of the residual is constant across the observation. This is the assumption. And if the heteroskedasticity is present, this means this assumption is not retained. Okay, this assumption is violated, and this means like the variance of the residuals are not constant. We have two types of heteroskedasticity: conditional and unconditional. If here we have x, here we have the error term. If the variance is increasing, then this is known as the conditional heteroskedasticity. This is conditional heteroskedasticity. And if the variance is like this, here it is low, again the variance is increasing, again low, and again variance is increasing. So there is a consistency, like you can't say, okay, so for the higher value, higher variance, lower value, lower variance. Here we have higher variance here also and here also, and here we have the lower variance. Yes, it is not constant, it is changing, but you can't specifically say like, okay, with the higher values there is a higher variance. You can't say like this. It is changing, the variance is also changing. If this is the this is the nature, then we will call this as unconditional heteroskedasticity. Okay, let's see. Unconditional heteroskedasticity is when the variance is not related to the level of the x variable. Okay, that is the higher or lower value of the x. That is an independent variable, right? This is violation, but not the problem or significant problem in the regression. So we will call this as, okay, yeah, this is the violation, but we don't have problem with this. If there is unconditional heteroskedasticity, we will go on with the testing of the regression model and forecasting. However, if the heteroskedasticity is conditional heteroskedasticity, then variance is related to the level of the x, and is the violation as well as problem in our regression model. Now see what happens in the model. Effects on the standard error. S stands for the standard error. And remember, standard error is used in the t-stat calculation. And here again, I'm assuming you already understand the hypothesis testing part. This is unreliable. First, this results in the type 1 error if the data is financial data. Okay. The next is here, the F test is unreliable. We used to test T test and the F test. F test gives the combined testing of multiple coefficients, right? So the effect on the hypothesis test is F test is unreliable. Then effects on the coefficients are reliable. Remember this. There is no impact on the coefficient, but you can't go ahead with the hypothesis testing. That's the problem. How to detect this? And you have to detect this either with the scatter plot. See this? We use the scatter plot, or the BP test, Brush-Pagan test, which is the chi-squared test. Okay. And here we will discuss the Brush-Pagan here. Now, how to correct this heteroskedasticity? Again, we don't have methods here. This much is given in the curriculum, this much is given in the notes. So we are discussing this much only. Okay. You have to remember it. How to correct it? Calculate the robust standard error, also known as the correlated standard error, or H heteroskedasticity consistent standard error. And these standard errors can then be used in the t-stat using the original coefficient, because your coefficients are reliable. So you don't have to deal with the coefficients. So use the original coefficients For the t-stat calculation, use this standard error instead of the original standard error of the model. Fine. This is the heteroskedasticity. How to do the calculation of the robust standard error or the edge consistent standard error, we don't have that discussion in the curriculum. Now, next is the serial autocorrelation. Serial autocorrelation violates the assumption. The assumption is error terms are independently distributed. If there is a serial autocorrelation, this means the residual terms are correlated with its lagged value. This means if I tell you the previous correlation, previous residual term, based on that you can predict the next residual term if these two are correlated. And the ideal assumption is like it should not be correlated. Okay, you should not be able to predict or gauge the value of the residual term. The residual term is correlated and not independent. This is the meaning of serial autocorrelation. And what it is violating, the error terms are independently distributed. This is the assumption which is violated. Now see what happens. If it is positive serial correlation, S stands for the serial correlation or autocorrelation. It is one and the same thing here. Positive serial correlation is like when the positive residual increases, the probability of observing positive residual in the next period. If the serial correlation, because it's correlation, it can be minus and plus, right? The negative and the positive, it can go up to -1 and +1, right? If this is positive, if assume like the serial correlation is the positive serial correlation, then it will lead to a problem where the positive residual increases the probability of observing the positive residual in the next period. Fine. And the reverse is true for the negative serial autocorrelation. If the serial autocorrelation is negative, then it increases the probability of observing the negative residual in the next period. Fine. Now, negative SC results in SC being too small, that standard error being too small. This is the impact on standard error. Again, the reverse is true. So effect on standard error, it will result into too smaller the standard error. If the standard error is too small, then your t-stat, because it is a dividing term, remember, it will be too large, and same is for the f-stat, because in f-stat also we will use that. So f-stat and t-stat both will be too large, and again it will lead to type 1 error. Okay, I assume and like I hope you remember and recall the type 1 error then, because it was in the level 1 also and level 2 also. Now, effects on the coefficients. What are the effects on the coefficient? The coefficients are consistent. Remember this. The coefficients are consistent if the lagged y is not used in the model as x. Just a second. Y is equal to b0 plus x1 b1, b1 x1 plus b2 x2 plus, here you are using b3 y t minus 1. This is the lag. This is the using lag dependent variable in the model as x. We are using x as in the independent variable. So you're using the lagged value as an independent variable. If you don't understand what is lagged term, then we have the whole discussion on the lagged value in the time series chapter. So for now, just remember, lagged value is taking the data one step back. Okay, so if you have say past 100 days, so from today and past 100 days, so lag value will be from yesterday again 99 days. Okay, now you are comparing the 99 days past and 99 days the current. Okay, so this is the lagged observation, that is t minus 1 day back. Again, your whole series is same. And again, if you don't understand the lagged part, we will discuss this in detail in the time series part. And for now, you can just remember the content. Inconsistent if the lagged y is used in the model as x, that is a independent variable. So if you use the lag dependent value in the independent location, as an independent variable, then your coefficients will be inconsistent. So remember, it can be consistent if it is not used, that is a lagged y is not used. If it will be inconsistent if the lagged y is used in the model. This happens in the time series model, and again, the regression is also like the time series also regression only, but with the time series data. Okay, now how to detect this? The single lag is detected using the Durbin-Watson test. If you want to detect the single lag serial autocorrelation or serial correlation, it can be done using the Durbin-Watson test. And if you want the more general approach, you want to test the multiple lags, then we have the Bush-Godfrey BG test. Okay, Bush-Godfrey BG test. How to correct this? Again, the same thing. The correct using the calculate the robust standard error. This is like known as the New Way West correlated standard error or edge consistent error. And then same, you can use it in the t-stat, assuming this is the situation that your variables are consistent. Okay. Next is the multicollinearity. And here we have relationship with the omitted variable. Multicollinearity is the situation when the x variable are not this is the assumption that the x variables are not exact linearly related between any two or more x variables. We are talking about the exact linear relationship, and this is the assumption. If the multicollinearity is present, this means the independent variables are highly correlated with each other. In the omitted variable, we said correlated. Here, we are looking for the highly correlated. If the independent variables are highly correlated, then there is a problem, and this is the violation of the assumption. And the assumption is it is not exactly linearly correlated. What will happen to the standard error? Your standard errors will be inflated. It will be increased. Due to inflated standard error, it will increase the probability of the type 2 error. Here, your standard error was too small, the type 1 error increased. Here, the standard error is inflated, lower t-stat, more type 2 error. Consistent but imprecise and unreliable coefficients because of inflated standard error. Okay, and then how to detect this? How to detect the multicollinearity exists in the the model. The sign is like when the t-test shows none of the individual coefficients are statistically significant. That is, none of the coefficients are contributing to the model. Your t-test is showing this, but f-test, when you do the combined testing, at least one of the coefficient is statistically significant and r square is high. Okay, for the f-test, r square is here, the r square is high. F-test shows at least one of the coefficient is statistically significant, and t-test shows none of the coefficients are statistically significant. Okay, so this is how you detect it. The second method is quantifying using the VIF. VIF stands for the variance inflation factor, which we will discuss later. We will discuss GB, GP, VIF, Durbin-Watson, everything later. Okay, then how to correct this? Correcting is very simple. Identify your highly correlated independent variable, omit it. Omit one or more correlated x variables, or use different proxies for x, or increase the sample size. Why you can increase the sample size? Because this is consistent. Remember, the coefficient consistent means as you increase, remember this, the coefficient consistent means as you increase the sample size, you will get the better accuracy. Because here the coefficients are consistent, you can always correct your model by increasing the sample size. Okay. Imprecise and unreliable part will be gone by increasing the sample size. Okay. So I hope you understood this particular part. Now let's talk about the Bush-Pagan chi-square test. Again, here you don't have to focus on like the every detail of the BP test. Just understand it on the from the exams purpose. Okay, the limited discussion is there even in the curriculum. Now first, BP test procedure is here. What are we doing the BP test? Remember, BP test is for the heteroskedasticity. That is identifying the relationship, in summary, identifying the relationship of the residuals and the independent variable. That's why we use the regression of the squared residuals, where the squared residual from the original regression, the first model, your model, original model, and regress this on the original set of independent variables. Obviously, this is what we want to find out in the heteroskedasticity. That's why we will run this regression. Here, the thing is, the test statistics is calculated using the BP chi-squared test statistics. And this BP chi-squared test statistics is n into r square of the residuals. You will get the r square of the residuals using this. That is a regression of the squared residuals. And here the degrees of freedom is the k degrees of freedom. K stands for the number of independent variables. N is simply the sample size. Remember, BP test is the one-tail test. Now, rule, if this is the rule in the red, remember this. If your T stat from the BP test statistics is greater than the T critical value, T critical will be provided in the exam, T stat, maybe you have to calculate, again, this is very easy to calculate, okay? You will reject null, remember it. You have to remember it like this, T stat. This, remember, this is the total value, okay? Absolute value of the T stat greater than the absolute value of the T critical value. If it is negative, then you have to still take the absolute value only. Reject the null, and this means the conditional heteroskedasticity is present. What about the unconditional? We can't comment about that. BP test is not for that. But here, remember, T stat greater than T critical means you will reject the null. If you reject the null, then conditional heteroskedasticity is present. Remember it like this. Example is very simple. Here you have the R square of the model. Let's say 15%, using n is equal to 36. We are taking 36 months, and significance level is the 5%. Okay, 5% significance level. Degrees of freedom, we are taking 1 degrees of freedom. So T critical value, one tail critical value using the chi-squared distribution. Remember, the BP test, the Bush-Pragan test, uses the chi-squared distribution. Here, the T critical value is 3.841. It will be given. Okay, you can't do the calculation. And T statistics is calculated as n into r square. R square is given here, n is equal to here. 36 multiplied by 0.15. You will get test statistics or T stat equal to 5.4. T stat is greater than T critical value. You will reject the null. Conclusion, conditional heteroskedasticity exists. Fine. I hope you understood this particular part. You have to remember it. Okay. Now, next is the Bush-Godfrey test, BG test. And we are using BG test for what? To test the serial autocorrelation. So here, ideally regression should happen with the self. Self as in the residual, not with like yourself. Okay, now this is the more general approach that can detect the serial autocorrelation at the multiple lags. We also have the DW test, Durbin-Watson test, but I am covering this DW test in the last. Reason is DW test is not discussed in the curriculum but used in the question. That's why I'm covering this DW test in the last. You have DW test here, you have DW test in the time series also, but in none of the section, in curriculum, in notes, nowhere the DW test is discussed in detail. So I will just give you the rule book for the DW test or applying the DW test, which will be sufficient for the examination. Okay, but first we will see whatever is given in the curriculum. Based on that, we have to first like understand this. Okay, now we have the BG test. The procedure is, because remember we are testing for the serial autocorrelation, regress one regression residuals on the original independent variable plus additional variable representing one or more lagged residuals. This model will look like y is equal to b0 plus b1 x1 plus b2 x2, assuming these are from our original model, plus you have, let's say, p1 error term t minus 1 plus p2 error term t minus 2. So we are taking the lagged values here. Okay, we are taking 2 or 3. You can take like 10 lagged values, no problem. But here we are taking more than one, because if you have only one lagged value, then you can easily do that with the DW test, Durbin-Watson test. But here we are taking the 2 lag values. So we are talking about this. Now again, we will read this statement. Regress original regression residual on the original independent variable plus the additional variable representing one or more lagged residuals. Fine. I didn't like, this should be like this, error term. Okay, I used y by mistake. The model should be b0 plus b1 x1 plus b2 x2 plus p1 error term t minus 1 plus p2 error term t minus 2. Okay, like this. So remember this. This is the model. You don't have to remember the model. You have to remember like what are we doing in the BG test. Regress the original. I'm reading this again and again so that it sticks in your mind. Regress the original regression residual. Regress the original regression residual on the original independent variables, on the original independent variables, plus or addition, in addition you have to also take the lagged error terms. Okay, so this on this, like this. Fine. Now here, your null hypothesis is P1 is equal to 0. That is not statistically significant. This means the coefficient of the lagged value is not statistically significant. And alternate is the coefficient is not equal to 0. Alternate is coefficient not equal to 0. Coefficient of what? Coefficient of your lagged value. Okay. So if you get this equal to 0, uh, if you, in simple terms, if you reject the null, serial correlation is present. If you reject the null, that is P1 is not equal to 0. If you reject this, this means that your error term, lagged error term, have some serial correlation with the original error term. If you fail to reject, then this means no serial autocorrelation. Here P is the slope of lagged error term. Test statistics. The BG test statistics follows the F distribution with P and N minus P minus K minus 1. Degrees of freedom. P is obviously number of lagged variables, K obviously independent variables, and sample size minus 1, right? Degrees of freedom, where here everything is provided. Now the decision rule is, you have to focus on the decision rule. T-stat, very difficult to calculate in the examination, don't bother about it. T-critical will be provided in the examination, so don't bother about it. Okay, just remember the decision rule. The decision rule is T-stat greater than the T-critical value. This means you reject the null. This means serial autocorrelation is present, like this. Okay, T-stat rejected, this means reject the null. This means serial autocorrelation is present. In exam, you may find this situation very difficult, like if the T-stat is greater than T-critical, should we reject the null or not reject the null? Maybe you remember, we reject the null. After that, if you reject the null, this means, like, what does this mean? Like, is the serial correlation present or not present? That's why I'm saying, remember the decision rules. T-stat greater than T-critical means reject the null. This means serial autocorrelation is present. Fine. Next is the VIF factor, variance inflation factor. And the variance inflation factor we are using for the multicollinearity part, right? Now here we want to test the multicollinearity. Is there any correlation between the two independent variables, or maybe the one independent variable is highly correlated with the other independent variables? Okay. First approach we already discussed, using the t-stat. That is, t-stat test shows none of the individual coefficients statistically significant, and on the other hand, your F test shows one of the independent variable is statistically significant and the R square is high. Now how to apply the VIF, variance inflation factor. Now this VIF quantifies the multicollinearity. Obviously we know there will be some collinearity. We discussed this in the omitted variable only, right? There should be some collinearity, but how to quantify it? What collinearity, multicollinearity is the huge multicollinearity which is causing the problem in our model? That we have to see here. First, the procedure is regress one of the x with the other remaining x variables. This means your model will look like this. x1 is equal to b0 plus b2 x2 plus b3 x3. You have to follow this regression model now. From this, you will get the r square from the equation, and then you have to use this in the VIF calculation. And VIF, variance inflation factor, is calculated as 1 divided by 1 minus r square. R square. This r square is written in terms of, remember, this r square is written in terms of the percent decimals. Okay. So for example, let's say you have 30, coefficient of determination is 30%. So 1 minus 30 divided by 1. So this will be your value. So if you do this, 1 divided by 0.7 is equal to 1.428. And remember, r square in your model, that is x1 is equal to b0 plus b2 into x2 plus b3 into x3. If you use this model and you have high r square, this means that the x2 and x3 is able to determine the value of the x1. This means high correlation. If you recall the CFA level 1, where we discussed the r square is nothing but the correlation, but if you take the under root of it, if you take the square root of r square, you will get the correlation, right? So again, this r square represents the correlation. Then we will see, okay, there is a strong correlation. Fine. So this is how you calculate the VIF. VIF calculation is simple. One more thing. If R square is 0, this means x2 and x3 is unable to determine the x1. So this will happen and your final VIF will be 1. If VIF is equal to 1, the variable is not highly correlated with the other x. Variable is not highly correlated with the other x. Remember this. I gave you explanation because R square is very like low or 0. If VIF is equal to, or sorry, if VIF is greater than 5, that is, remember, VIF greater than 5 is the result of R square greater than 80%. You can do the calculation. Just simply do this. 1 divided by 1 minus 0.80. If you simply solve this, you will get the 5. Okay. Very simple. Then the further analysis is required. You can't say, yes, there is multicollinearity. You can't say there is no multicollinearity. Okay. And if the VIF is greater than 10, that is, this is coming or happening because R square is greater than 90%. This indicates the significant multicollinearity. Significant multicollinearity. So in exam, if you get a question or the situation where you are provided with the VIF and the question is, which situation indicates the significant multicollinearity, which independent variable is significantly multicollinear, and VIF is presented for the different models for the x1, x2, x3, x4 like this, then remember you have to simply go for the VIF greater than 10. Very simple. Remember it. Things will be easier for you in exam. Next is the Durbin-Watson test. As I said, I don't know, like I have thing to say here. I don't know, maybe I'm missing something, but I was unable to find any write-up on the DW test in the level 1, level 2 both curriculums. Okay. The write-up was very basic write-up. Okay. So it was provided in the form of solution for the question, and don't know like why is this. So I'm providing DW test from my side, and just remember the conditions of the DW test. DW test stands for the Durbin-Watson test, and here we use it to detect the first order serial autocorrelation in the error term of the regression. We discussed, right? So DW test and the PG test. So DW test, when the one variable is there, the first order autocorrelation is should be tested, and DW test is not very useful in this regression chapter. This is useful in the time series, very important in the time series, because ultimately this is related to the time series only. But we are discussing this here because it is given here. Okay. Test statistics here. Again, don't bother about how to calculate the DW test statistics. DW statistics ranges between the 0 and 4 by default. The very nature of the formula is such where your T-stat, that is the test statistics, will range between 0 and 4. Value of approximately 2 suggests no serial autocorrelation. Remember it. There is no other alternative. Remember it. Even if you see the questions in the end of the chapter questions, if you remember it, you will be able to deal with those questions. Okay. Because explanation is not required. Value of the approximately 2 suggests no serial autocorrelation. Approximately 2, no serial autocorrelation. Value significantly below 2, positive autocorrelation. Value significantly above 2, negative autocorrelation. Remember it. Below 2, positive autocorrelation. Above 2, negative autocorrelation. Approximately 2, zero autocorrelation or no serial autocorrelation. Procedure, you don't have to bother about it. Interpretation. Here, the null is no first order serial autocorrelation exists. This simply means like t minus 1. If we have to write it, your h0 will look something like this. Not important for the exam, just giving you from my side. Okay, so h alternate will look like t minus 1 not equal to 0 like this. Okay. Alternative hypothesis is first order serial autocorrelation is present. Compare the calculated DW statistics against the critical value to determine whether to reject or fail to reject. Okay. You have to do this if the critical value is provided, but the general rule is this. This is the general rule. In real life and mostly for the exam also, you have to follow these rules because the optimal critical value is 2 here. Okay. Based on that optimal critical value, we decide this. Here we have, it is like you have to determine the critical value. It is giving you the impression like you have to determine the critical value. First, it will be provided in the examination, and generally it is 2. Okay. Even in the real life, it is 2. Considerations, the test is specifically for the first order autocorrelation. Remember this, and it is most appropriate for the time series data where the first order observation is meaningful and not very important for this. Okay, important for detecting the serial autocorrelation, but not important, very important for this chapter. Okay, so that's all for our module number 3, model misspecification. Thank you for watching this video. If you have any queries, feel free to ask me, because I'm uploading this video, I'm telling you, for the, like, the YouTube audience. Okay, thank you, bye bye, take care.